One of the things I want you to be aware of is that your textbook uses parentheses in its vector notation, which, most textbooks would not do because it just confuses people with between a vector and an ordered pair, which means a set of coordinates. Yes, there's a lot of similarities between them, the difference being that an ordered pair or a coordinate is just one point in, a plane or even space or whatever that matters. Whereas a vector represents a movement or a directional force from a origin to that location. So, and the location kind of helps us find a way of calculating the magnitude and the overall direction of the force. So even though there's some similarities between what we do when we plot a point and when we determine where a vector is, they're not the same thing. We use the greater than and less than symbols together as kind of like a bracket, and you're gonna see that as we go through this. Primarily as our notation for vectors, and that's why it's going to be seen on your tests, quizzes, the web work assignments, and just about any other textbook out there. For some reason, Axler had to be different on this front too. So keep that in mind as we go through this, because if you read anything in the chapter dealing with vectors, it may confuse you because they might be talking about a vector when it looks like they're discussing an ordered pair. But basically, vectors, there's two types of vectors. You have a horizontal vector and you have a vertical vector. The horizontal vector used to be called I. So this one up here, if I get my drawing tool working properly, which is always sometimes not a given thing that will happen here. So this vector that goes from 0 to 1 to 1, 0 on the x-axis, we would call that the I vector. Not to be confused with the I we're going to be using for complex numbers. And this is what we would call the J vector. And more importantly, we would put this bar above it if we're handwriting it to indicate a vector. And then, if it's typewritten, it's usually written with bold, as you can see down there. If you handwrite it, you use a bar, and then you always have this debate about should the bar go above the dot on the I and the J, or should it replace the I and the J? And there's different textbooks that handle it differently, to the point that some people would exhaustively talk about it, which is really not necessary. It's just the same thing. But we don't primarily use the I and J notation very much. We use the brackets, as I mentioned before, to kind of signify a vector. The whole idea behind a vector is it's made out of a horizontal and vertical component. So, anything at an angle, it's going to be based off of how far horizontal and vertical I go in movement with respect to each other. That'll determine more or less the direction of the overall vector. So when they say to draw a vector, and you do more drawing of vectors when you get into physics, because science teachers like talking about the head-to-tail method and drawing vector diagrams, where some of those vector diagrams are really not necessary, because if you just mathematically add the vectors together in a lot of instances, you got the what they call it, the resulting vector or the resultant vector, and then if you want magnitude and direction from that, it's a lot easier just to get the resultant vector and find the magnitude and direction of that rather than trying to draw a figure and being accurate about your angle measurements. But if I wanted to draw pictures of these, I'd set up a coordinate system. Of course, I'd mark it off in some way. And here I'm marking each one of these going by each tick mark you see represents a unit of 1. So if I wanted to draw vector A, which is 3i plus 5j, which would also be known as 3, 5 with the vector brackets around it, basically you plot a point at 3, 5, you draw an arrow leading from the origin and ending at 3, 5. And of course you put the arrowhead at 3, 5. B equaling 3i minus 2j. I would write that as vector. Another way we would write that vector is 3, negative 2 in the vector brackets. But again, I plot the point 3, negative 2. I draw the arrow leading from the origin to that point. The same thing with negative 6, 1. Not a whole lot of difficulty in drawing a vector. And generally, if I was doing two vectors acting on each other, I would draw one vector, and at the head of the first vector, I would draw another coordinate system and draw the second vector, starting as at the arrowhead of the first vector as its origin. They call it the head-to-tail method in physics. Vector operations here. Here you're asked to do the following operations. You're asked to draw a picture of the resultant vector. For some reason the R got cut off. Then I want you to find the magnitude of the resultant vector. Well, if I take the vector u, notice it's written in bold, and multiply it by -2, I just multiply the two parts by -2. It's just like having, negative means change direction. The 2 means I have two of these vectors, one starting as the other one ends. So I'm going to have a vector that's twice as long. So it's going to be at -4, -2. It means it's going to head in the opposite direction. So as far as the drawing goes, again, I'd plot a point at -4, -2, draw the arrow from the origin to that point. As far as the magnitude goes, the magnitude of the vector is represented by the length of the picture. Now, I don't have to have the picture to do that, because essentially if I was doing, find the length of that arrow I just drew, I could use the Pythagorean theorem again. So if I just take the two parts of the vector and use the Pythagorean theorem on it, and do the magnitude. Now, magnitude looks like I have these double bars in place of absolute value symbols. And most textbooks do use the double bars, whereas other textbooks use single bars. I think Axler actually uses the double bars, which is one of the things he does do that's consistent with other textbooks. I have seen other textbooks just use a regular absolute value symbol, with the understanding that the person who's watching or doing the work realizes that if they're dealing with a vector, that means magnitude is comparing to do an absolute value. Be it as it may, I would just perform the Pythagorean theorem on the two components of the vector and come up with the magnitude. So in this case here, it would simplify and rationalize out to be 2 times the square root of 5. 4u plus 2v means I'm going to do 4 times the vector 2, 1 plus 2 times the vector 1, 3. Of course, as before, I'm just going to multiply those numbers through and get 8, 4, and 2, 6 as my two vectors. Now, when I add two vectors together, or subtract for that matter, all I do is I add the first components together and I add the second components together, or subtract, whichever the case may be. So I'm going to add the 8 and the 2 to get a 10 in the first position. I'm going to do the same thing with the 4 and the 6. So the magnitude, so this vector is going to be 10, 10. Drawing that, it will look something along the lines of that. As far as the magnitude goes, just perform the Pythagorean theorem using 10 as the two leg values. I'll get 10 times the square root of 2 as my overall rationalized vector. U minus 3v. Again, I'm going to have the vector 2, 1 minus 3 times the vector 1, 3. Of course, I'm going to follow my order of operations. So I'm going to do 3 times the vector 1, 3. Now, I tend to keep it all as addition, because any addition problem can be made into a subtraction problem and vice versa. So I'm going to consider more of adding negatives than subtracting, positives. So the vector becomes, because I'm multiplying through the -3, I have the vector -3, -9. So I have, interruption from little Tyke. So I have the vector 2, 1 plus the vector -3, -9. So again, I'm just going to add the two components together. So 2 plus -3 becomes -1. 1 plus -9 becomes -8. So I have the vector -1, -8, which will look something along the lines of this. I have it scaled by 2's there. So as far as the magnitude goes, I'm going to perform the Pythagorean theorem on those two components and get the square root of 65.